Phonetically correct, the best kind of correct.
Hello, welcome to Security, Cryptography, whatever. I'm Deirdre. I'm here with David. How are you doing, David?
I'm doing great. I've organized my drinking for the rest of the evening, so after this is over,
Excellent.
It's smooth sailing.
Excellent. Wonderful achievement for your day. I'm very proud of you. Thomas, how are you doing today?
Here.
Cool. Also, special guest, George Tankersley. How are you doing, George?
Hi, I'm doing great.
Cool.
This was very short notice.
This was very short notice. We short notice got George to hop on the pod with us today because we were spitballing about what we wanted to talk about and include things like deprecating SRP, secure remote password agreement. Is that what that stands for?
Yes.
Yeah. And in terms of deprecating SRP, in favor of a modern PAKE, password agreement, key exchange, something like that, George knows a lot about the things that we need for those sort of protocols, such as oblivious pseudorandom functions and other things that have to do with anonymity credentials that George has worked on. So we just pinged George and asked if he could hop on a call with us.
The other thing that happened was we decided we were going to do a news roundup today because we have to do something, and apparently no news has transpired.
I mean, there's been a few iOS 0-day kernel vulnerabilities that got patched, but you know, we've talked about that several times in a row.
3 episodes about that at this point.
There's an Apple patch day. There is a 0-day exploit in one of their platforms due to memory unsafety. The sky is blue, water is wet.
We should do an episode this time about things we're somewhat qualified to talk about.
Like PAKEs?
Sounds good to me.
Somewhat qualified. Checks out.
Mm-hmm.
A couple days ago, on the front page of the Orange site, which is the source of all the topics for this podcast, I think a Matt Green article on password-authenticated key exchanges just charted at the top of the site. And a week earlier, a friend of the podcast, Steve Thomas, had posted, I'm stopping myself here because it's occurring to me that I'm sure he's Steve Thomas. It's been one of those weeks where I've forgotten everyone's name. His first name's definitely Steve. It's Thomas. I'm right about this. Steve had written an article about...
No, you're Thomas, dude.
Yes, that's true. Steve had written an article about why you should never use SRP anymore. And SRP is like the most popular password authenticated key exchange. So like a password authenticated key exchange is like you think of a cryptographic protocol where you're initiating the protocol and setting up session keys, like with TLS based on certificates, right? Well, TLS uses certificates to set up those keys. So you do a Diffie-Hellman with 2 made-up keys on either side of the connection, but you can't trust those keys because a man in the middle could also just make up 2 sets of keys for either side of the connection, then proxy, and you'd never know just straight up Diffie-Hellman whether or not you were talking to the real person you thought you were talking to, or whether your key was the man in the middle's key. So certificates are one way of solving that. Triple Diffie-Hellman with a long-term static key is a way of solving that problem.
And then like signal.
Right. And then for a lot of reasons, kind of a construction that gets a lot of attention is password authenticated key exchange, where again, we do like something resembling Diffie-Hellman, but to like break the tie between whether we're talking to a man in the middle or whether we're talking to the real person we think we're talking to, we use our password, right? So you could think of a password authenticated key exchange as like, I'm going to do Diffie-Hellman, but my secret or the Diffie-Hellman protocol or some part of it is dependent on my password. And the exchange will only complete if both sides agree on what the password is. That's roughly what a PAKE is, right? And then again, like SRP is this like protocol from the 1990s, which was the first popular password authenticated key exchange. Part of that is because a lot of the good simple PAKEs were patented for a long, long time. None of that matters anymore. All those patents have expired. But for a long time, SRP was the one you could use. And Steve wrote a post about SRP. So I guess like things to talk about here, we could go through a little bit of the logic that Steve uses. I think it's interesting to point out that people shouldn't use SRP, if only because on that Orange site thread about PAKEs, more than one person suggested that they were considering implementing SRP. And if you listen to Steve, there's no good reason ever to do that anymore. But also just, I get the attraction of password authenticated exchanges. I get why people like them. I think part of the reason that people like them is because you can get your head around what they're doing and they seem clever. And that's kind of an insidious combination, right? Like if you've got something that's clever and that you can understand, you'll latch onto it, because a lot of things that are clever and hard to understand, you don't feel like you understand them, and so you don't talk about them that much. But PAKEs, everyone kind of gets.
Like textbook RSA. It seems so easy.
Yeah.
My first question was going to be, why don't you just do Diffie-Hellman and then AES encrypt a password on both sides? And the answer is because that's trivially man-in-the-middleable. That's what I'm hearing? So this is why we have PAKEs. Okay.
Right. You can do other things, right? You can have an enrollment secret, like when you set up your device. Your device can register itself with a long-term static key. And then you can do Diffie-Hellman, or triple Diffie-Hellman with that static key, and not have to use a password or anything else to break the tie, because you have another long-term key to do that. That's a lot of what you see when you see people talking about the noise protocol framework. That's really what they're trying to do, right? Is, I want to set up a session based on a long-term cryptographic secret that I have, and also have some kind of forward secrecy, so I'm not just dependent on that one key. That's noise, right? That's the idea behind noise. But yeah, if you just did Diffie-Hellman, did the encryption, and then set your password, any man in the middle could starve your password.
Yeah, and so we're kind of assuming that we've somehow pre-shared a password, but not pre-shared a long-term static key of some form.
Which makes sense. It fits people's mental model of how I sign up for a service, I enter my password. In that one exchange, the server has my raw password, right? Like anytime I set myself up, and that's not generally true of PAKEs, but like in your normal security modeling, when you're thinking about the service, you register with a password, set it up that one time. And then from that point on, the server has something that it can use to verify that, you're using the same password as you've always been using.
George, what were you going to say?
I was just going to say, this is all in a category of stuff that Filippo and I once called Crypto 1.5 in a talk. It's the things that PAKEs, blind signatures, stuff like that's been around for a long time, and that everybody looks at and thinks like, oh, I understand what's going on here. That's cool. It's just like half a step beyond something I'm familiar with from TLS. Where can I possibly use this cool new crypto thing? And, that kind of remains an open question, but it's very attractive to play with.
Especially when they were originally written up, usually based around either finite field or factoring assumptions or things with RSA. And then you revisit them, kind of like the work you've done with, you could just do this now with elliptic curve groups and make it faster and smaller and actually deployable.
Which gets to a problem with SRP, is because the formulas for SRP is a simple protocol, but it was designed in the 1990s, and the formulas for SRP use the Diffie-Hellman group that it's working on. So
pure Diffie-Hellman, not just a group.
By the way, I'm going to pull the group here because I have this problem every time I write about this stuff, right? What is the term that you use to describe kind of classical, simple, multiplicative group Diffie-Hellman?
Finite field Diffie-Hellman.
Yeah.
That's what I say.
It's FFDH,
So we just call it
finite
FFDH.
field Diffie-Hellman, or just DH if you've already started using ECDH somewhere else.
Okay, so just to be clear for people who don't follow the math here, right? But your kind of your textbook RSA, or your your crypto tutorial, or your applied cryptography description of RSA or Diffie-Hellman, where you just generate a prime number and then, raise numbers to a power modulo that prime. That's finite field Diffie-Hellman.
Yeah.
And we have that distinguisher because it's much more common today to not use finite field Diffie-Hellman and instead use elliptic curve Diffie-Hellman. Yeah. Which is pin compatible. They're the same ideas, right? But you're using a different mathematical group, and it's your keys are much shorter and the algorithm is much stronger, right? So when we talk about
There was
FFDH,
there was no need to distinguish between Diffie-Hellman and anything else, because the original was just over a field of integers. And then when elliptic curves came along, and it's like, no, this is a elliptic curve group that we're using to do Diffie-Hellman, then you had to start distinguishing it from the old one. And so that's kind of where the finite field Diffie-Hellman came from.
Okay, and if I'm trying to piece this together axiomatically in my head, so why is FFDH, why is finite field the good description here? Can I not use that term to describe what I'm doing with elliptic curves?
No, you cannot, because if you're using a field of integers, you have more than one operation over the algebraic structure. you have a multiplicative operation and an additive operation. With elliptic curve groups, you only have the additive operation. And basically it boils down to, why are elliptic curve groups considered a more secure primitive to build stuff on than just the scalars or whatever? It's because there's a strictly less algebraic structure of the elliptic curve group to exploit by an attacker. So therefore you're able to make your key sizes smaller. And this is sort of the basis of why the attacks are slightly different, and why the strength of elliptic curve groups is basically better, because there's strictly less stuff mathematically, algebraically you can do with the elliptic curve group, as opposed to the field of integers between like 0 and a prime.
Gotcha. Okay, that's perfect.
Do fields
right?
have divide or just inverse?
That's the inverse operation of multiplicative operation.
Yeah. Okay. And rings just have
I think
adds and
rings,
multiplies without
rings
necessarily
have
inversion.
inversion.
This is Math 512 at the University of Michigan. We're happy to teach abstract algebra here today. My name is Robert Lazarsfeld. 3 people found this joke hilarious.
We're sticking with this though, right? Because I'm going to get this nailed down and be good for the rest of my life, right? So like it goes, groups are the simplest thing, right? And groups just have, with finite fields, it's just or with a classic multiplicative group, Diffie-Hellman, whatever, it's just the multiply operation, right? And then one step above groups is rings, right? It's not field next, it's ring next, right?
I think
and
so.
then one step past,
because it's over a different closure for the different operations between additive and multiplicative. And I think fields are the ones that it's like both of those operations are over the full closure, and rings are not. And I forget which one of them it's not.
Rings can have 0 divisors, which is why everything breaks, because you can multiply 2 non-zero numbers together in a ring and get 0. So it's like the numbers mod a not prime. For example, like the numbers mod 6, if you multiply 3 and 2 together, you get 0. That would make it a ring instead of a field.
This is great. This is great. Now I know abstract algebra.
And it turns out that having 0 divisors and having an inverse for everything are like mutually incompatible. Cool. So it's one of those if and only if things. So that's how you tell if something's a ring or a field.
Okay, so like one of your problems with SRP as a 90s protocol was that it was written with, kind of finite field integer arithmetic, and it haphazardly uses both the multiply operation and the add operation in its formulas, which means it's only usable, those formulas are only usable for kind of classic finite field, integer, whatever's. Because elliptic curves can't do the addition trick that that they need in the protocol.
And that's not to be confused with scalar multiplication, because scalar multiplication over an elliptic curve group is just the additive operation of adding points together. Scalar number of times. So
which, just to bring this all back to earth, is you can't instantiate SRP directly over an elliptic curve.
Right.
So that's one big problem that people have with it. It's not like it's hard to argue on a message board that that's a deal breaker, because it's like arguing no one should use RSA anymore. It's true, but it's not like clearly obviously true.
Right.
The other big problem that people bring up with SRP is that it leaks information in the protocol when you run it. So you're using passwords, and you're effectively creating a hash of the password. It's not a hash, it's a verifier or whatever, but like you're creating an artifact that verifies the password from the password, and that needs to be randomized, because otherwise you could just pre-compute them all and have a dictionary and use them, kind of immediately attack anything. So I hate the term salt, but the verifiers in SRP are salted.
It's not really a nonce, it's a salt.
I use nonce, but when this comes up, just because when you talk about salts, then people invent new kinds of salts, and they want to put salts all over the place. And like, I'll say randomized. This is randomized. It's not salted. It's randomized.
Pink Himalayan salt.
Yeah, Thomas, when should I use kosher salt versus granulated salt?
Is pepper permissible?
So I'm gonna credit my partner with this, but like, why is pepper on the same level as salt? Like, pepper flavors things, and salt is a mineral. It helps you cook stuff. Pepper's just a spice that like has a high opinion of itself.
If you have a low flavor palette, salt is also a spice. It does give flavor.
Yeah, if you grew up in the Midwest, salt counts as a spice.
And usually when you see pepper tossed around, it's a secret salt. Like, there's the normal salt, and then there's the secret salt, the black salt, which is what pepper is. And like, that's what they call it, is they call it a pepper. And it's a stupid idea, and you shouldn't have secret salts for your password hashes. Anyways, SRP has these, and the protocol, when it runs, leaks the salt. So before you've proven that you have a password, before you've established a key an attacker who's querying a server can get the salt for a particular user.
Oh yeah, I'm
which
looking at this
sort of
diagram
kind of
and
defeats.
That's
It kind of defeats the purpose of salting. It might be the case that you almost might as well not salt, I guess, at that point. Because the point of a salt is not just that you have to compute lots of different things, is that you have to compute every possible salt into the verifier to pre-compute. But if you can get the dictionary of everyone's salts, then you've drastically reduced the amount of pre-computation you have to do. So it's like, it's an incremental step instead of, huge multiplicative exponential amount of extra computation. So people don't like SRP. SRP sucks. Steve would also point out that there's ways of implementing SRP there are bugs in SRP implementations that are really common that leak the verifier directly. So you could run the protocol with the state machine out of step a little bit and get the verifier, which is like compromising a password hash for a user. It's like if you could talk to a web application and get somebody's password hash from it and then just crack it offline. That's a mistake that happens all the time. I'll point out also that for SRP, another really common mistake is just getting the math wrong. One fun thing about all these finite field, public key things is there are often bugs that will zero out the computation.
Oh no.
So you can provide a parameter in the protocol that's either 0 or, kind of more insidiously, the prime itself or a multiple of the prime, which will work out to 0 because everything's mod prime, right? Yeah. And if you don't check for that, the computation zeroes out and you can predict the result because it's 0, right? Which is really bad for Diffie-Hellman. And you've seen vulnerabilities in VPNs and stuff like that for, TLS or for IPsec or something where it's possible to zero out, the Diffie-Hellman computation. It doesn't matter, I guess, that much because, both sides trust each other in those protocols. And so, it's like one side is opting out of security for their connection, but that's all they're really doing, right? And it's bad, but it's not the end of the world. In SRP, it's the end of the world, right? Because if you can zero out the computation, it doesn't matter if you know the password or not. So you can bypass password authentication. Anyways, there's lots of bugs with SRP. People don't like it. And Steve kind of proposes a bunch of alternative PAKEs that have come out of patent, but have kind of the same vintage as SRP, but they're sanely designed and simple protocols that curves fit into. And there are a couple of different knobs on these things. There are different kinds of PAKEs. There are balanced PAKEs and augmented PAKEs. And there are also PAKEs that use oPRFs and PAKEs that don't use oPRFs. And here I fall off the cliff of my knowledge with, I've read a Wikipedia page on what an oPRF is, but George, you actually know what you're talking about here. So tell me, explain.
I think I live in a very concrete oPRF world, but I could talk to you about specific protocols, but I think in general, you can describe an oPRF as a way of calculating a keyed hash over an input where the person holding the key does not learn the message that they're hashing, and the person who receives the output does not learn the key. So it's you see with oPRFs, you see a lot of these services where there's some flow where the user blinds a message and then submits it to a server who in various ways and for various reasons will emit a deterministic random output that can then be unblinded and used. And this turns out to have a really surprising number of uses in the world.
Privacy pass?
Privacy pass, you can do it for anonymous credentials. You can do it. You can do private set intersection like this. You can do all kinds of password hardening type stuff.
So a PRF is just a keyed hash. So HMAC SHA-256 is roughly a PRF, right?
A PRF is more general than that, but that is one you can instantiate.
Okay, and then
it's any pseudo-random function. So most cryptographic hashes qualifies for this as well, whether they're keyed or not.
The key part is the oblivious part in this context.
That's the O, right? But the PRF part of it is just, I take a hash. A hash by itself is not a PRF, but a construction that hashes a key into it or a secret into it turns that hash into a PRF, right?
You can use a quote-unquote regular cryptographic hash as slotted in as your pseudo-random function, depending on what you're trying to model in your security model for your protocol.
Because they're parameterized over a key. When I look at a PRF, the notation, it'll be PRF sub X or something like that, where X is the secret. There has to be some secret involved, right? I could just be totally wrong here, by the way. This is great.
I think it depends on your proof. If for some reason you can say The adversary already doesn't know what your input to this hash is. You don't really need there to be a key. Like, you could just feed data into it. And I think that would count as a PRF for any hash that you could use to make an HMAC.
This whole time
but it's pretty much always an HMAC because you need to keep something secret.
So like this whole time I've just been like mentally substituting when I read papers, like PRF, oh, that's like HMAC, whatever. Or,
but not
HMAC
necessarily. For example, in Zcash, there's like a whole bunch of PRFs all over the place, and they're all different instantiations of Blake, but it's literally just sort of like domain separator. I am using, this is for my keygen, like stick a domain separator byte string at the front and then put in everything else that you're hashing as your pre-image and then spit out the image. And that is your use of that specific instantiation of that hash function as your PRF for this particular case. And literally all it is just like adding a byte string at the beginning of your pre-image to do domain separation. And that counts.
Yeah, domain separators, by the way, are fun cryptographic shibboleths. You can make it look like you know what you're talking about really easily just by sprinkling them all over the place. It's like a bad cryptographic protocol won't have domain separator strings, but like look at WireGuard sometime or Noise, and you'll see that like part of the protocol, like the version of the protocol or the particular algorithms you're using or whatever, are passed in as strings as input.
Yeah.
And they're literally part of the protocol as domain separation.
Yep.
The idea being like, you don't want a bug where like an output from one part of the protocol gets leaked or spit out somewhere and it could be reused in some totally separate part of the protocol.
Yep.
And like we've seen crypto bugs that are like that. And you can break all those bugs just by every time I use, HMAC. Okay, it's not HMAC, it's HMAC sub this string, which just means that string's hashed into it. Now I have like a special, version of the family of HMACs, which just works here.
Yep.
That kind of like sort of cross-session or cross-protocol usage comes up in oPRFs a lot because of the blinding. And so you find yourself either shoving your policy into key management or motivating a desire for a partially oblivious PRF, which lets you have a domain separator.
Oh, yeah.
So like in my mental model, and it's not complete because I know nothing about oPRFs, right? Except for what you've already said. But it's like, imagine I had a web service that could HMAC things for me against some key or whatever. Actually, that's dumb because you can already imagine that service. But like, imagine some algorithm where like I'm the caller into the algorithm and I have some message I want to HMAC, but I don't have the key and I want to produce the output without the key. And the oPRF allows somebody else to, they contribute the key, I contribute the message, but neither of us get the other person's thingy.
Yep.
How does that work?
With algebra.
Moon math.
Go on.
Moon math.
Yeah. No, it's not moon math at all. It's Diffie-Hellman. Your ingredients here are basically Diffie-Hellman and some kind of hashed group.
Okay.
You take your input, you hash it to the group, you generate a large random exponent or scalar. You blind your hashed message using that. You send it off to the server, who essentially, you could say that they sign it with their key, or they, do their part of the Diffie-Hellman or whatever. And basically they multiply by their secret scalar as well, that they send that back to you, and you multiply by the inverse of your blinding factor, and there you go. You've got an obliviously evaluated PRF.
So this strictly relies on the commutativity of these operations.
Yep. It is the same as Diffie-Hellman. In fact, the main oPRF that gets deployed is called 2#DH.
Well, it also relies on the existence of an inverse, which regular Diffie-Hellman does not rely on.
Right. There's no inversion in classic Diffie-Hellman, either over a finite field or elliptic curve. In this case, you're dividing out your value, which does work. You just don't see it in regular Diffie-Hellman.
So the blinding thing here is just like I come up with a random value before as the person with the message, I come up with a random value and kind of multiply that in beforehand, which obscures my actual message from the other person. They can't get it because it's been obscured by this blinding random value that I put in. And the algebra here is just when I get the result back, I just divide my random value out of it again. Am I right about that?
Yep.
You have a weird face on. I could just be totally wrong.
Oh, I think you got it.
George is afraid to tell me that I'm wrong.
No, that's exactly it.
So hash to group. When you deployed privacy pass, was that hash to P256?
Remind me privacy pass.
Oh,
Deirdre, what is Privacy Pass?
Privacy Pass is a way for you to, it's basically a way for you to solve CAPTCHAs and get around these, like, if you ever saw a site hosted by Cloudflare and you were trying to access it over Tor, and they're like, we don't know who you are because your IP address is indistinguishable from anyone else who's used this IP address from a Tor exit gateway. We want to do something that's like solving a CAPTCHA, but still preserves your anonymity because you want to be able to like change your IP address or whatever, but still assert that you are someone who has solved a CAPTCHA before privately or with anonymity. And Privacy Pass was initially, I think, a browser extension that worked with Cloudflare terminators or edge locations that let you do this using anonymous credentials, so that you were able to solve a Cloudflare CAPTCHA, get a set of anonymous credentials out of it, and then no matter how you accessed Cloudflare again from either the same Tor exit gateway or any other, you would just hand them an anonymous credential and say, no, I am not a bot. I am not a spammer. I'm good to go. But it did not link anything about you or your IP address or the thing that you solved, just that you had solved it and you have an anonymous credential to attest to that fact. Is that right, George?
Yes. So the thing that Privacy Pass adds on top of this oPRF evaluation flow that I've just described is that later when you hit an edge service that wants to that would otherwise give you a CAPTCHA, instead you can reveal one of your hash to group pre-images along with the like signed point, and then the server can say, okay, if I take that pre-image, I hash it and I sign it myself with my key that I know but you don't. If it matches, then it's valid. And in practice, what we actually do is use that element to key an HMAC that macks the request.
Got it.
That's Privacy Pass.
Did that ever get standardized? I think there was a draft.
There is an awful lot of IETF activity that came out of Privacy Pass. There's the VOPRF draft. There's a Privacy Pass working group.
Yeah.
There's portions of Hash to Curve and Ristretto were arguably motivated by like the needs of Privacy Pass and related protocols.
Yeah.
So, is it standardized? Like, no.
Pieces like an arm and a leg and an eye are all independently getting standardized.
Yeah, but not for lack of effort.
Okay.
It's just that the wheels of CFRG grind slowly.
Indeed.
Unless like standardization is like your dream and your thing. This is the ideal way to interact with the IETF, where you do something and then other people deal with standardizing what you already did while you move on to other things.
Yeah.
Did that use hashing to P56 or what? I forget.
So none of that existed
Right.
at the time.
Right.
In any way other than in that original like Breyer or Tibochi paper or wherever it is, the simplified SWU stuff. So I think it's actually rejection sampling.
Oh, I see.
I think we just like hashed something repeatedly until we got a valid X coordinate. Yeah,
Okay.
hash and pray.
Cool. Hey, if it works, it's not the most elegant in terms of a construction or a proof, but if it works to make this thing work with general security, it's a win.
Yeah, I mean it's fully deterministic. It's just inelegant and statistically might fail.
Right. Yeah.
Like we're in heavy math territory here right now, right? So like for people that are not read into this, like I know what hash to curve is, but I'll pretend not to and say, what's the big deal with hashing to a curve?
That's a question for
George.
George.
I can help because we're using it in several things, but if you want to go, George.
Yeah. So when you think of like a normal cryptographic hash function, the output of that is just random bytes, right? The idea usually is actually to project whatever your input is into this like uniformly distributed space of bytes in a way that's difficult to predict and difficult to reverse. And you ideally want there to be no structure whatsoever.
And indistinguishable from random.
Right.
And like any like sequence of random bytes is also a number, right? Like it's, if I need it as a number somewhere else in like a protocol that races things to powers or whatever, they're all just numbers. Like they're all fine numbers, right? But they're like not fine.
They're
curve
good
points.
numbers, Brent.
But they might not all be fine numbers,
Right.
is where hashing to curve comes into it. If instead of big random integers that might or might not mean anything, you actually want like valid coordinates for a point on your specific elliptic curve, then you have to do something different.
Mm-hmm.
That's broadly hashing to curve, and
Yep.
there are different ways of doing it, and they're different they're actually the part of elliptic curve math that actually uses algebraic geometry.
Mm-hmm.
Like the fact that you're talking about an elliptic curve and not just like a fast way to implement a group begins to matter because you're hashing to the actual curve.
Mm-hmm. So, for example, hash and pray is trying to use the numeric style and try to just try and hope and cross your fingers that it turns into a valid point on the elliptic curve group that you're trying to use. So you literally will hash something, turn that into a value that can be the x coordinate of a point on this elliptic curve group, and hope that that x coordinate, when plugged into the elliptic curve equation, gives you a valid point with a y coordinate, and it's the one in the group that you actually want to use. That's basically hash and pray. And if it doesn't work, you try and try
you just
again.
bump a counter. Yeah, you like bump a counter
Exactly.
and hash again. Okay,
Yeah, that's hash and pray.
The more correct name for it is try and increment.
Yeah. But I remember I heard hash and pray. I'm like, I know exactly what you're doing. Using a real hash to curve solution, yes, uses the algebraic properties of the group and uses things like isogeny maps from your input set, your pre-image set, and using a actual map that uses the algebraic properties of the curve group and the structure that you're trying to image into to make sure that you actually get as best as you can a uniform distribution over the set of points in your group, so that when you actually use this as a PRF in like your crypto protocol or your security proof, it is actually like not just sort of a wink and a nod, a pseudo-random function. It is much, it is an unbiased as much as possible pseudo-random function, as opposed to hash and pray, which is definitely not.
For 25519, this is
something like 1 in 4 or 1 in 8, like 256-bit numbers would be like a valid curve 25519 point, if I remember right.
Oh, that's
more or less.
That has a cofactor though. There's the cofactor stuff, and there's the hash and I don't know.
But yeah, hash and pray actually has like a really dense chance of success. I don't know why the number 10 is. I think it works out that we decided to just loop 10 and try it 10 times and like panic if that didn't work because we expected it to work in 2 or 3 at most.
Mm-hmm. For privacy pass, did the bias in the PRF for hash and pray matter at all for leakage or anything?
So I think we were doing it via rejection sampling with like slightly wide number or slightly wide hash outputs.
Okay.
To we did something along those lines to avoid it, but I don't actually remember.
Okay, so there was basically a mitigation to try to handle.
But yeah,
that. Got it.
You don't want to like take your hash output and then just like reduce it mod whatever. You do want to try again if it doesn't fall in the right range.
Okay.
This is also, and we'll edit this out if I'm wrong about this, but this is also Alligator, right?
Alligator is one of the algebraic hash to curves, yeah.
Right.
Or Alligator 2, the Mike Hamburg one.
Yeah, usually when people are talking about Alligator, it's usually in a hash to curve setting.
Mm-hmm.
My favorite part of Alligator is the logo, which is an alligator eating elliptic curve points and shitting out random
numbers. Yeah. Actually, I think Alligator goes both ways. It's both taking a curve point and giving a canonical encoding, and also taking a domain and have a canonical quote hash encoding to the curve points, if I recall correctly.
Yes, because it's what they used in one of those. Oh God, Eric's gonna slap me because I can't remember the name, but those anti-censorship things that piggyback on top of a TLS connection. Does anyone remember the name of these things? I should know because I sat next to the person who invented them.
It's Opfus proxy, right?
What?
It's the like Opfus from Tor, because the prior work to Alligator was Ian Goldberg's Uniform DH, which was less good for reasons I don't recall.
Huh.
But the idea was to encode it as a uniform bit string to stop deep packet inspection from killing your bridge handshakes.
Because in theory, even though deep packet inspection can't break the cryptography, it can still spot in the handshake things that have, P256 curve structure, right? Like you look at a number, it might or might not be a valid, curve point. And so if your string isn't uniformly random, if it's encoded to be an actual curve point on a specific curve, then you can spot it on the wire, is the idea there. And then that was when I read when I skimmed the alligator paper a long time ago, that was the motivation for it is, you can spot curve points, on the wire in traffic.
Yeah.
But you can encode them with the alligator map to be totally random. And I didn't care at all because it's not a interesting problem to me. But, in modern cryptography, I see alligator, invoked a lot for the opposite problem, which is I ran a hash, I have a random value, but it needs to be in this curve protocol now. So how do I adapt it into this curve protocol? So that's the alligator eating its shit and spitting back out curve points.
Yeah, and other hash to curve solutions beyond alligator, which are explicitly the opposite of give me a point and turn it into random. It's trying to take an input and the output, the codomain of that hashing is all the elements are elliptic curve points, but the distribution of that codomain is uniform, so that you can slot that in and say you should not be able to distinguish anything about the pre-image by the bias of the possible samples of this output.
Yeah, they also use it. I was thinking of refraction networking or decoy routing, tapdans and telex being the main examples of it, which is just another anti-censorship thing where it relies on a middle box to find a colluding website that's willing to help people get around censorship and then read something secret out of a TLS handshake with the benign site and redirect it to the blocked site. And they use alligator for that. But I don't know, maybe we could actually talk about what the hell opaque is now.
Oh, yeah.
Okay, first, does anybody here know what opaque is? Because all I know is that it's opaque and that it involves oPRFs.
I know a lot more about opaque than I did a few weeks ago.
Give us opaque versus other pakes.
Okay, so there's two angles on opaque, one of which I knew and caused me to discount it for years, and one of which is more relevant to my current interests. If you look at the libraries and the IETF drafts about it, is a way of using password authentication to generate secure session keys, right? It's a standard PAKE in that way, but it's also I believe they're called augmented PAKEs, in that there is a server helping you do that you're trying to authenticate to. So the way that works is you register with a server, you give it a encrypted blob using an oPRF derived key from your password, I believe. And that blob contains a private key for your client identity. And then later, when you want to log in, you run this flow that executes the oPRF and gives you the oPRF result and that encrypted blob. And if your password was correct, you'll be able to derive the key to decrypt the blob. And then you run an additional round of authenticated key exchange to get a new random full-strength session key with your counterparty server. And then that allows you to log into the website or whatever it is.
I think I understand opaque now. So I was going to say so SRP is in theory an augmented PAKE. And in my head, I know the term. And in my head, it's always been that augmented PAKEs are the ones where the server stores effectively a password hash and not the password itself, right? Not enough information for the server to run the protocol itself with the password. So if you broke into a server running an augmented PAKE, you wouldn't get the passwords. You'd get the verifiers for the passwords. You have to do a brute force computation against them. That's my only understanding of what it means to be an augmented PAKE, is that if you steal all the information from the server, you don't get the passwords. You just get effectively the hashes, or the thing you have to compute against to recover the hashes. And a balanced PAKE is the one where both sides could run the protocol. They have the passwords. So if you broke into the server running a balanced PAKE, then you could dump all the passwords. Is that a crazy way to look at it?
No, that's correct. And actually, there's a portion of the like IETF version of opaque where the user gets a hardened key derived solely from their password that the server never sees, and that is what the new WhatsApp end-to-end backup system uses to encrypt the backups.
Yeah.
The password is never seen by the server in an opaque execution.
And that WhatsApp backup should be rolling out to iOS and Android devices. So you can end-to-end back up your chat records on your Google Drive or your iCloud, and it is independent of anything that the iCloud or Google Drive does on their own,
So
which is nice.
do you need like a third party to run something like this correctly, or just like HSM that you've thrown away the admin key for, or is none of that required at all? Or am I completely confused? That's possible.
I mean, the opaque spec leaves a lot as an exercise to the deployer, and like key management is certainly one of those things. WhatsApp seems to be using like fleets of HSMs. In blockchain world, we do or likely would instead use like a threshold implementation of opaque.
Oh, fun.
But yeah, for opaque, because it is in that like augmented class, you do have this asymmetry between like one party who's expected to be like storing some state and to be online and responsive all the time, and like one party who is not. Whereas in a symmetric PAKE, like with Magic Wormhole, both people have to be online.
Mm-hmm.
I think like Apple also famously uses a PAKE in this exact same setting for iCloud keychain. So like the secrets that you vouchsafe in iCloud keychain, they're unlocked with your phone PIN. And so to prevent you from sending your PIN through to Apple where they could just read the PIN and then recover your secrets, what they do instead is they store all your secrets, or they store a key that, I don't know what exactly it is, but like they store all your secrets effectively chained to a fleet of HSMs. And then you speak the protocol that you use in iCloud keychain effectively speaks SRP from your device, from your endpoint, which you control, directly to their HSMs. So
I think the pin on your device is combined with the burned in large key with the secure module, the secure enclave or whatever of each device.
Yep.
So it's not just one or the other. You have to combine the two. But yeah, like they're using that to unlock the things that they are storing on their fleet of HSMs. And that was considered very good until China leaned on them to deploy very specific HSMs that are very specifically located in mainland China for Chinese Apple users. So
that's bad.
It is bad.
That's why I only like American-made HSMs. Even though many HSMs are actually Canadian, but
It's just like a box that takes a smart card or whatever.
You also, I think we see PAKEs in like the new Wi-Fi protocol has a kind of controversial
Isn't
PAKE
that a
in it, the
terrible
Dragonfly
PAKE?
PAKE.
Is this Dragonfly?
This is Dragonfly.
Yeah.
So like you see PAKEs in settings like this, like if I'm setting up a fleet of HSMs and running a custom protocol to do iCloud keychain, a PAKE kind of makes sense there, right? Same with whatever WhatsApp is doing. Same with like, logging into a wireless network where I use a password to log into it because people can't remember AES keys off the top of their head. They're fun to talk about. They make a lot less sense in other applications where like the much more sane thing to do is to have an enrollment key, like an actual genuine AES key or something that roots the security for your system, where like you don't really need to remember something off the top of your head. Or if you do, you only need to remember it locally to like decrypt a key, and then the protocol itself just runs with keys.
I think the WhatsApp thing basically splits the difference because they do let you use like I think it's like a 64 byte or 252-bit just byte string. You can have a very long password or basically equivalent of AES key. Or they can help you generate one, and it's like basically up to unlock the key that they store in their HSMs or something like that. They let you be like, I trust myself to generate a very long, high entropy key, and I am solely responsible for managing this key, and or the easier option for if you want some backup reliability.
This has been good. I feel like I sort of understand opaque now, and I definitely understand oPRFs. I thought oPRFs might involve polynomials, which is where my brain turns off in all cryptography. I've decided that I do all the cryptography that doesn't involve polynomials, which is why I don't do anything with GCM.
I mean, technically,
And
elliptic
so
curves
now-
are polynomials.
Quiet. And then, so this oPRFs are now on the other side where I could conceivably think about understanding how they work, which is great.
Yeah.
So this has been very good.
Yeah, they're crypto 1.5.
Yeah, they don't involve pairings. Like biscuits needs pairings, right? No pairings for this.
I think we're going to have Jeffrey Capri on to tell us that biscuits does not need pairings anymore.
I don't think they ever
They came up
actually
with-
need pairings, to be honest.
Really?
But Biscuits 2 was going to get, I think, much simpler. But I think Biscuits 1 does not have pairings. You'd think I would know because I deployed it in production the other day, but I didn't actually. I was like, I'm Jonathan and Jeffrey are smart. I'm sure it's fine.
You're actually using biscuits?
We use Biscuits in production for one use case where we have some endpoints that are called by like a mobile devices. And then we have an admin panel where we can do things. And sometimes the read-only versions of those endpoints, we don't want to duplicate the logic that's like, show me all of the X for this user that would be shown to them in the app. So we have a credential system that can issue credentials for specific endpoints to an employee to then be able to make a call as if they were a user to do something like to make a GET request to a specific endpoint. And so we're able to encode the endpoint, the person that you are impersonating through the support panel, as well as the employee who is doing the impersonation, all gets put into the credential, and then that can be verified on the other side. So you can be like, no, you're not allowed to have impersonation credentials for actions that actually change something, or
That's awesome.
and then you get the audit logging of like, oh, hey, like Dadrian did at name tag did this, and Ross at name tag did that.
Mm-hmm.
So I'm curious how pleasant they've been to work with.
So they took a little bit to like get, once you figured out kind of how to write the verification, they've actually been nice because we then extended them for one other use case where we needed to issue a blind credential to the mobile app that would then be used to authenticate the next call it would make. And like, I wasn't even online. Like I was out the day that someone else did this, and they were just like, oh, this is really easy. And like, just added in the thing and made the verifier work. So that was good. But what was complicated was doing things like getting the username that's in the token out of the token, for example, is a very silly looking function. It's just very silly. It's not like crazy or it's not like impossible to figure out. It's just very silly looking. And you kind of had to put some constraints on it to make it constraints from like a programming perspective, not constraints from a Biscuit perspective, to make it work in a way that wasn't like 10 million lines of code every time you did it.
I have to ask you one other question about your Biscuit implementation, which was, how did you unit test them?
So we actually did. So I did on the podcast say that you should always test the failure cases.
Mhm.
And so while we do have a verifier that like does specific things, one of the tests for it is actually kind of a duplication of some of that verify code, and that we just call the Biscuit verification directly. But what we do is we repeatedly call it, and we provide like more information each time, and then we make sure that it fails until you get to the last time. So it doesn't check every possible like combination of like, will this work or not? But it will do the basic things and be like, are all of these getting passed without the information? We test that only the last verify, or we've provided all of the data, does in fact verify, and the rest don't. And then we have some other
That's
tests
awesome.
as well. But this is really only used by like the support panel, and not the mobile apps themselves don't use it because they can't hold it uses Ristretto as the underlying credential, and that's not something you can put
Nice.
in Apple's TSM or TPM.
George is in victory.
We don't do that there. If we do start using them with the mobile app, what we'll end up doing is like signing nonces inside of the biscuits using like the ECDSA key on the app.
Cool.
Okay, what is a biscuit?
A biscuit is just a macaroon where the policy language is data log and the crypto is, I don't remember what the crypto is, but they're not using HMAC. They're using asymmetric crypto.
Great.
I don't know if that makes it easier, if that answers your question.
No, not really, but this link probably will.
You know what a macaroon is?
Yes, I do.
So biscuits are just the new macaroons. Like they're the
But
super
they need
cool.
pairings.
They don't actually use pairings. I don't remember.
We thought
what
they
use.
did.
It's like, imagine that you wanted to do macaroons, but entirely with public key crypto. So that you'd get the public key distribution story, but with macaroons, which are purely symmetric key. Like biscuits are what they came up with to do a public key, like first class public key version of macaroons is sort of what it was. And like they were trying to figure out what the right because it's easy to chain an HMAC, and it's less straightforwardly obvious how to chain signatures. They're doing signatures. Yeah. So it's less straightforward to chain signatures. So they were talking about, I think, pairing curves as one solution for the actual concrete implementation of biscuits. And now it's just straight up signatures.
And I think it'll become even less moon mathy signatures in the next version, if I remember correctly. We should really get Jeffrey on here to explain this to us.
Yes.
We were asked to have takes on unit testing, but what might also work instead is just, you said ristretto, and we could just demystify crypto terms for the entire thing. So I'm imagining that there's lots of people here that would not naturally do the baby fist pumping motion when they hear the word ristretto. So somebody take it away.
Me, I like telling the whole story because we've come full circle. So in the beginning, when elliptic curves became a thing, not just in academic papers in 1985 by a guy named Koblitz and Miller and whatever, they standardized mostly prime order curves. The most popular one, I think, in the world is P56, and this standardized prime order curve over a 256-bit field. This is the one that's used by almost every TLS, ECDH handshake. If you ever see ECDSA signature in the wild, it's probably P56, and if it's not, it's P384. It's probably the second most popular curve in the world is probably now the Bitcoin curve, SecP256K1. Also a prime order curve, but it's a Koblitz curve. Once upon a time, the best formulas that we had for doing all of these operations on elliptic curve group elements were called incomplete formulas. That meant that, like, if you added 2 points together that were different points, you would use one branch and do a different set of math. If they were the same point, you would do another branch and a different set of math. And if one of them was the identity, you would have yet another set of math. This made implementing elliptic curves a little bit fragile. And the elliptic curves that we had were not super fast. Once upon a time, someone came along and said, hey, there are some curves that are Montgomery and Edwards curves, and we have complete formulas for them, and they're faster. So look how fast they are, and the math is better. There's no corner cases or edge cases. Just, make sure that you factor out this little cofactor, which might be points of order 2, 4, or 8. And I think Thomas would be able to tell us about the whole class of attacks that he's able to leverage against small order points in your protocol. This is where the popularity of things like Curve25519, Ed25519 signatures came from, is from these extra fast, but with better formulas, elliptic curves. The better formulas, however, came with cofactors. It's not nice when you have to slide assume a prime order group into your cryptographic protocol, and the prime order group is a subgroup of this elliptic curve group, and then you have another subgroup that's very small, and you have to do all this kind of hand waving and juggling to make sure that you are, in fact, operating over the prime order group and not accidentally this non-prime subgroup that gives you very weak points on your elliptic curve operation or your group operation. So someone decided, I think it was Mike Hamburg, that came up with a technique called decaf, which basically takes these cofactor curves like Curve25519 and others and turns them into a prime order group, always, full stop, whatever, so that you can always map points on Curve25519 or Ed25519 onto, or you always have a canonical encoding. So you're never operating over the cofactor group. All the points will always operate, and all the group elements always operate over the prime order group. You get the speed wins, you get the complete formulas, and you get the assurance that you are, in fact, operating over a prime order group. So there's been kind of pressure in the crypto fans of elliptic curve community, I guess, to move towards this very nice construction so that if you want a fast, complete prime order group in your cryptographic protocol, instead of using these cofactor curves, use ristretto. However, in 2016, someone published new elliptic curve formulas that are complete, for prime order curves, like short wire source curves, like P256, and they are very fast. So do we even need to use these cofactor curves anymore? Do we even need to use Ristretto anymore when you can just do P256 with these new formulas that don't have all the branching, that don't have all these edge cases, and are pretty damn fast, and you just use that as your prime order curve in your prime order group? So we liked Ristretto. Ristretto was very nice, but we may not even need it anymore. The end. George, anything?
I think do we even need it anymore is a matter for the benchmarks.
Sure. Oh, that's a good point. Yes.
And the, full-on Henry de Valence implemented, Ristretto, Dalek, Rust curve code is still pretty scary fast.
Yeah. Yeah.
Yeah, you can also do parallel versions of the Edwards formulas, which I think are also only implemented in that library.
This is this is relevant for signatures, right? And not for the Diffie-Hellman. So my question is okay, so we have complete formulas, much better formulas for the P curves now, or for P256 or whatever, right? For all the short wire Strauss curves. So the question of whether we still need the cofactor curves, of which 25519 is the most famous, right? The big motivator for me on curve 25519 is not having invalid curve points you have to deal with in Diffie-Hellman protocols. Those are scary vulnerabilities. It's where you run an interactive protocol that does Diffie-Hellman with with a curve. And if you can have invalid curve points in your protocol, if I can inject that a parameter as a client talking to a server or whatever, and then learn things about the underlying secret from them, that's classically when we look at vulnerabilities, those are called invalid curve point vulnerabilities. And 25519 doesn't have those vulnerabilities. The new formulas don't mitigate that problem, right? Or I'm not following how they would.
I'm doing a quick grep, and I don't think it explicitly calls out mitigating that. I think you're correct. Ristretto does basically elide the entire both invalid points because it's curve 25519, so that the underlying set that it is using doesn't have them. They are not defined, but also the entire subgroup of small order points is also just eliminated. That will never be representable as a valid Ristretto group element. But I think you're right. I don't think that the formulas. So what's interesting is that I feel like, I don't know, George might be able to help me out here, but the formulas are nice, but even so, yeah, I guess it's one less thing you have to worry about with at least curve 25519 is that you will never be able to get an unrepresentable point. But I guess with P256, you can.
Wouldn't Ristretto be giving you the guarantee that you don't have to deal with the invalid points? Because all the points are valid. It's just with 25519 and Diffie-Hellman, all you have to do is mask off the first 2 bits or whatever, and then problem solved. And so it's
you can't meaningfully attack those protocols.
If you have a Ristretto group element, then you have a Ristretto group element. There aren't any special classes of bad ones. The point, I talked earlier about speed, and that's fun and all, but the actual point of Ristretto is to present the abstraction that protocols expect. And, this matters a little for Diffie-Hellman and signatures, but it actually matters a lot more when you start trying to do anything more complicated than that. So, zero knowledge proofs or anonymous credentials or, even more complicated kinds of signatures. The little abstraction gap starts magnifying the complexity of everything you do. But so the point being that you don't have to worry about most of these things if you're using Ristretto correctly, which the specs and the libraries go to some pains to help you do.
My unfrozen caveman lawyer understanding of this, which I'm, from everything you guys have said, I'm guessing I'm somewhat wrong about this, but it was the Monero vulnerability is what I'm thinking about here, was preserving a one-to-one relationship between documents and signatures. Right? There isn't more than one possible signature, and that the cofactor in 25519 or in ed 25519, if you're not implementing carefully, gives you the possibility of multiple valid representations for the same signature. And that having the pure Ristretto group or the simple prime order group or whatever means that you naturally won't have opportunities for that malleability. You can't have, I'm getting this wrong in some regard, but like that was my basic idea of what the motivator was for when people talk about Ristretto. It's I want to build complicated signature systems and make sure that it's a 1-to-1 between the input and the signature. So I'm guessing I'm wrong about that.
I think you get that for free from Ristretto, but I think maybe George can correct me, but I think the Monero one was what Zip 215 solves. Was that?
Which one's Zip 215?
The one that actually specific versions of libsodium, like the ed 25519, ed DSA.
Oh, the validation criteria thing.
Yes. I don't recall, but
yeah,
I think it sounds like that.
It might have incidentally fixed that.
Right.
Like if we'd had that bug. But my memory of the problem with the Monero bug, and this is not at all guaranteed to be correct either, but it was actually a mismatch between like the algebraic notion of the key the key and the signature that it produced and the like byte-wise encoding thereof. What they were doing was like to prevent double spins, they were like hashing the key, with like SHA-2 or something on the assumption that it would be like 1-to-1, like this key produces these signatures. But in fact, with the cofactor malleability, you can kind of like shuffle those around and you get like 8 different potential representatives of the same like class of valid key signature pairs. And like obviously those are all like concretely in terms of bytes, different points. So if you're, if you're actually hashing them, you will end up with multiple different identifiers that can spend the same funds.
Yeah, I'm rereading the Ristretto site, and it's basically, yes, that the fact that basically you use an isogeny map from the entire set of possible ed 25519 points, you mod out the 8 cofactor, the order 8 cofactor, so that you have like 8 points and they all map to a canonical encoding of a Ristretto group element. And so that you cannot have that sort of malleability attack. You cannot have more than one point that is used in a signature, because there is only one. There is only one valid element and one valid representation of all of those 8 points. So yes, I think to come back to Thomas, you are correct. This is one of the motivators for Ristretto. Mm-hmm. But now I'm extremely curious about whether the new formulas help at all with the fact that you can define a point on an invalid curve for P256. Is curve 25519 twist secure? Ed 25519 is twist secure, right?
Yeah. I think it is, because, in the kind of like original DJB spec ladder formulas, like as one might find on a mailing list somewhere in undocumented Python, I think the point is that they just take the U coordinate and they don't care whether they're on the curve or the twist.
Right. All the math is completely dependent on the X coordinate. It's actually, if you whittle down all the math you need to do, it is not actually directly dependent on the Y coordinate. So as long as you're just on the quote unquote Kummer line, the projection of this set onto just the X coordinate line, it doesn't matter about, the other possible values. It's kind of cool.
Well, and I'll raise another point of order here about, in favor of the type of curve I happen to be most familiar with, the fields, the like underlying base field of the 255 curves is, chosen to be kind of like convenient and straightforward to implement.
Yeah.
Right? You get the very cheap reductions and stuff like that. Whereas when I have looked at P256 implementations, which is like primarily the giant blob of assembly in Go, in order to make them fast, you have to do much more complicated stuff.
Oh, you're saying that the field for curve 25519 is nicer?
Yeah.
Okay, I misheard.
So like the new you have these widely deployed like short Weierstrass curves, and that's fine, and we know how to make them fast, and maybe we have complete formulas for them now. But is it still going to be something that you necessarily like want to use? Does it have the same engineering trade-offs as one of the cofactor curves? Who knows? Depends on your situation and like who you are and what you're doing.
Yeah.
Because if you're working with a field shape such that literally, like this guy named Vlad who writes really fast code is the only person in the world who knows how to implement your field, well, that's not great.
Yeah. Huh. Why aren't there invalid curve attacks for curve 25519 as opposed to?
Because there aren't enough small subgroups in it. So like when you take if you take a random value, and so I'm probably, again, I have a perfect track record of this in this podcast of being wrong about things, but I'm probably wrong about this. But it's, if you take a totally random value over the possible space of the base field or whatever, like over the possible space of numbers there, you're going to land on a valid curve point. And I think there aren't enough small subgroups of it or whatever to actually do an attack against it. So basically all random strings are valid, or at least not attackable.
There's the step where you mask off a couple bits. And because you're only operating on the X coordinates, that fixes it off, I think.
Right. But even not doing that, like there's no practical way to attack that, right? Like, it won't work anyways, but I'm saying
Masking off those bits is just to eliminate the small cofactor points.
Yeah,
right?
which would be the points in the subgroups.
Yeah.
This is the whole clamping debate, right?
Yeah.
That's why I'm making a face. Let's not go down this rabbit hole. Viewers will not be amused.
Yeah. Well, I will say, like, this is one of the benefits of elliptic curves over finite field Diffie-Hellman is the smaller subgroups, but that's not, or the lack of small subgroups, but that's not entirely fair to say, because the real benefit is that someone has chosen a group that doesn't have small subgroups. You can choose a finite field Diffie-Hellman that doesn't have it. It's just, for whatever reason, when people do finite field Diffie-Hellman, they've decided that you should pick the prime at the time that you do it, which there are good reasons for, because if you pick a prime, if everybody agrees on a prime that's less than 2048 bits and like pulls it out of an RFC, it's probably been like broken by some intelligence agency. But
but those protocols aren't common, right? Like,
not anymore.
Like in like a dozen years of doing crypto assessments in like the 2000s, right? Like like Nate Lawson trained me to go look for, okay, can I propose Diffie-Hellman parameters, including, the group that I'm working over. And if I can do that, then, I have the small subgroup attacks and there's subgroup confinement or whatever we called them back then, right? And like, I never found that, right? That was not a real vulnerability for me in real systems, right? But it's not the case with the P curves, right? Like the P curves just naturally have, if you can propose a point that isn't valid on the P256 curve or whatever, it's like they're slightly, like, maybe it's 224 is the one that's really scary about this. I forget. But if you can propose an invalid curve point, then by doing that, you'll get enough information over iterations, like over like thousands of iterations, not zillions and zillions, right, to reconstruct the key with the Chinese remainder theorem.
So now I'm really curious
if
if this falls out of the bad formulas, or if this falls out of the curve that you chose. And my instinct
it's got to be the curve.
But does it? Because it sounds like if you're computing over a point that's not defined on the actual curve equation, then how are you computing over it? You must not be checking that you're on the right curve.
Using the smarter equations fixes it as a side effect of doing the validation that you would have done with the worse.
Yep. I've successfully been totally wrong about something.
There is one protocol that has proposed Diffie-Hellman, like user-defined Diffie-Hellman parameters. That's pretty popular. It's called TLS versions 1.2 and earlier. And it's just like the issue with that. And I wrote a paper with like Luke Valenta and Nadia Hennicher and a couple other people back in like 2017 or something about this. It's just that the RFCs that had defined groups for finite field Diffie-Hellman make no goddamn sense. And like nobody can agree if you should or should not have a subgroup in it. And the actual answer, like, you can just ignore the whole paper and just read the last paragraph of it where there's concrete recommendations. And it's just like, if you're using finite field Diffie-Hellman with a prime, pick a safe prime. And a safe prime is a prime where P-1/2 is also prime, because P-1 is always going to be even, because prime numbers are odd except for 2. And then over 2 gets rid of the even part. And so you want that to also be prime, because that means you will only have subgroups of order P-1/2, which is the max size, 2, and then, the full group of order P. and then everything's just fine. Like, you don't have to do point validation. Just make sure you're not getting 0 or something dumb.
This is logjam, right?
No, this is not even log. Logjam is just, what if we did number field sieve on your shitty 1024-bit primes and smaller, combined with the fact that...
which paper is this?
This is something subgroup something. Let me look it up.
Something subgroup something. David.
It is called Measuring Small Subgroup Attacks Against Diffie-Hellman. I contributed the measuring part, and people smarter than me contributed the small subgroups part.
I was going to bring up one of my favorite things, to be clear, that you can have a perfectly defined elliptic curve that has many, many small subgroups, such as a supersingular elliptic curve, which you wanted to have a smooth order so that you can use all of those small subgroups to use a subgroup as the kernel of an isogeny map. And then you do a map to a map to a map to a map to a map across a supersingular isogeny graph.
One does.
And once you have this, you can do post-quantum secure, in theory, knock wood, Diffie-Hellman-ish key agreement. But those curves are specifically chosen to be defined so that they have 2 independent subgroups. And all of those subgroups are full of small order 2, order 3 points, so that you can use them as generators of subgroups and you can define isogeny maps with them. But those are supersingular curves, and you should not use them for classical elliptic curve cryptography because they are incredibly insecure in that setting. They are explicitly for these specific post-quantum protocol constructions, but they do exist, and you can use them for reasons like that. Kind of similar to pairing curves, have specific subgroups with structure for these kind of different applications.
I have two things on the wrap here, right? So number one is, for the last month or so, I've been typing on a keyboard for my 2017 MacBook Pro. That's like QW6BTY. I've been like harvesting the keys from other keys around my house, and I finally ran out. And I bought a 13-inch M1, and it's smaller than the 15-inch I have, so it just sat on a shelf, even though the keys are falling off of this one. But they announced the 16s last week, and so I maxed one out, and it's arriving on Tuesday. Now, I bring this up not to talk about M1 MacBooks. Other than that, I think it's funny when I look down on my keyboard, it's just random letters. But like, because I'm one of those dorks who has like stickers all over their laptops, and I decided I needed like one giant-ass sticker to cover most of that laptop. And so I had made a bunch of giant ass stickers of our podcast art. We have the best art of any podcast. I think any podcast. I think every podcast of all the podcasts, our art.
People are
from
talking and people are saying we have the best art.
It's just the best. So I could only get a run of 50 of these, even though I only need one of them. So I have 49 giant ass stickers of our podcast art. So anybody that made it this far in the podcast and listened to Ristretto and oPRFs and all that, you can feel free to hit me up, and I will endeavor to eventually get you, a sticker.
Awesome.
The other thing I had to say was that my wife the other day pointed out that we've all been pronouncing axolotl wrong. That's not at all how it's pronounced.
What?
It's terrible, actually. So the TL at the end of a nahuatl word, the TL is one single consonant. It does not introduce another syllable, which is important because in those words, usually or almost always, it's the second to last syllable that gets the emphasis in the word. So when you pronounce it axolotl, you've also introduced another syllable, which shifts the accent to the wrong place. So people who actually speak that language, it sounds moronic to them when we say it that way.
It's actually pronounced like ashalot or something like that, right?
It's like a sholat.
A sholat.
Yeah, it's like a sholat. Second to last syllable gets the emphasis. It's like a sholat. And like the T is a weird sound. Like you have to like practice to do the actual T in the language, although it's somewhere between like a T and a CH. But even if you just did the T by itself, you'd be closer than axolotl. So never say axolotl. That was my other contribution to this podcast.
We're gonna be phonetically correct, and no one will know what we're talking about.
Phonetically correct, the best kind of correct.
Yes, absolutely. Okay.
George, thank you.
Yes, thank you so much, George.
Yeah,
Happy to have you.
No warranty express or implied on any statements in the foregoing podcast.
I am a cryptographer. I am not your cryptographer. I do not speak for any employers, current or former or future.
All of these comments are actually the opinion of your employer, the listener.
Who likely at some point in the past have paid Thomas for his opinions on security.
Archer Daniels Midlands, feeding a hungry world, and we're out.
Cool. Thank you. Bye.